Welcome back to Mr. AI Tech. If you're into artificial intelligence, future technology, and how machines are reshaping our world, make sure to subscribe to the channel. We break down complex tech into simple, powerful insights that actually show you what's coming next. Riassunto del video. In this video, we explore one of the most disruptive technologies of our time, autonomous driving. We start by looking at a world where cars no longer need steering wheels or pedals, and where AI makes every decision at high speed, even in complex urban environments. But behind this futuristic vision lies a huge challenge: the long tail of rare and unpredictable driving situations that still confuse even the most advanced systems. We break down how self-driving cars actually see the world, comparing camera-based systems like Tesla's approach with LiDAR-based systems used by companies like Waymo. Each has its own strengths, but also major trade-offs in cost and accuracy. Then we dive into the real intelligence layer: prediction. Modern AI systems don't just react. They anticipate human behavior in real time, using advanced neural networks similar to those behind ChatGPT. Finally, we explore the bigger picture: the business revolution. From robo-taxi fleets that could generate income while you sleep, to the shift from personal driving to full fleet management, autonomous vehicles are not just changing transportation, they're reshaping the entire economy. Outro, CTA breve. So the real question is not if self-driving cars will take over, but who will control the platforms that power them. If you enjoyed this breakdown, don't forget to like the video and subscribe to Mr. AI Tech for more content about AI, robotics, and the future of technology.
Welcome to today's explainer. We're diving into something today that is essentially an invisible, almost magical layer of technology. It's completely changing how machines interact with our physical world. Think about it. From that quiet little robotic vacuum kind of humming around your living room right now, to those wildly advanced self-driving cars navigating super complex city streets, there is this hidden intelligence powering literally every single move they make. So we're going to decode exactly how these machines actually see, how they map out their surroundings, and how they make these crazy, life-saving decisions in just a fraction of a second. It is an absolutely fascinating journey right into the algorithmic brain of modern robotics. Let's get into it. But hey, before we get into the really heavy tech stuff, let's start with a classic puzzle. Imagine waking up in a pitch-black, entirely unfamiliar room, right? How do you actually find your way to the door? Well, you reach out, you touch a wall, maybe you bump into a piece of furniture, and slowly, step by step, you start to build this mental map of the space. But here's the ultimate chicken on the egg problem for robotics. How does a machine build a map of an environment if it doesn't know its own location within it? And on the flip side, how does it figure out where it is without already having a map? Honestly, for decades, this paradox completely stumped computer scientists. Okay, let's dive into this. Section 1, the art of orienting oneself. The foundational algorithm that researchers eventually came up with to solve this whole mapping paradox is, well, it's nothing short of brilliant. The answer to our chicken or egg problem is called SLAM. That stands for simultaneous localization and mapping. Now, it's pretty crucial to understand that SLAM isn't just one single, piece of software you can just buy off a shelf. Actually, scratch that. It's more like a broad technological concept with infinite variations, relying on some seriously complex math and sensory data. Think of it as the actual algorithmic brain of a robot. It takes in this constant, non-stop stream of environmental measurements and uses them to simultaneously build a map of the area while also pinpointing exactly where the robot is standing on that very map. To truly wrap your head around SLAM, think about what happens when you get lost in a new city. First thing you do, you scan your surroundings for a landmark, maybe a super tall clock tower or just a really unique building. Second, you kind of calculate the distance. You figure out roughly how far away that tower is from you. And finally, you update your mental map. As you keep walking, you keep glancing back at that clock tower to see how your position has changed. Well, SLAM does exactly this, just computationally. It finds static landmarks, figures out its position relative to those markers, and continually, and I mean continually, updates its digital map as it explores. Which brings us to Section 2, LiDAR, or seeing with light. So a brain is pretty useless without eyes, right? SLAM algorithms are incredibly smart for sure, but they need raw data to process. They need a concrete way to measure the physical environment around them. Now, what's really interesting about this is how exactly LiDAR acts as the ultimate measuring tool in completely unknown spaces. LiDAR stands for light detection and ranging. Instead of just taking a flat 2D picture like your phone camera does, a LiDAR sensor rapidly shoots out literally millions of invisible infrared laser pulses. It then measures the exact time it takes for those tiny light pulses to bounce off objects and return to the sensor, a method known as direct time of flight. And because it brings its own light to the party, so to speak, rather than relying on ambient sunlight, LiDAR functions flawlessly in pitch-black darkness, creating these insanely accurate 3D point clouds of everything around it. And guys, the sheer scale of this technology is staggering. Top-tier automotive LiDAR systems, like the ones used by autonomous vehicle pioneers such as Waymo, don't just see what's directly in front of the bumper. No way. They can detect objects up to 300 meters away. That is a massive distance. To put that into perspective, when a vehicle is cruising at highway speeds of 60 miles per hour, that immense range is absolutely critical. It buys the SLAM algorithms the precious milliseconds they need to recognize an obstacle and safely react long before a human driver ever could. Let's move to Section 3, SLAM in the home and the operating room. Let's look at how this core concept builds out into some vastly different real-world applications. First up, domestic robotics. You ever wonder why modern robot vacuums don't just blindly bounce off your walls anymore? Well, it's because they use 2D SLAM. They actually map out your living room, remember exactly where they've already cleaned, and safely navigate right around your feet and furniture. Pretty neat, right? Now, contrast that everyday household chore with advanced medical surgery. In the operating room, doctors are using highly sophisticated 3D SLAM. By putting autonomous tools inside the human body, surgeons can map and navigate around dynamic, moving human organs. This gives them a real-time bird's-eye view of internal issues, allowing for incredibly precise operations without needing massive, deep incisions. So whether it's vacuuming your carpets or performing life-saving surgery, the core principles of localization and mapping are exactly the same. Moving on to Section 4, autonomous vehicles in real time. Now let's scale this whole narrative up to its most complex, chaotic application yet, totally unpredictable city streets. And this brilliantly illustrates how an autonomous car actually pieces together the world around it. You see, it doesn't just rely on one single sensor. It uses something called sensor fusion. The vehicle literally combines data from a bunch of different sources to create this complete 360-degree awareness bubble. It uses cameras to read traffic signs and see colors. It uses radar because radar can easily punch right through rain, fog, and snow to track the speed of other cars. It uses our good friend LiDAR to create that ultra-precise 3D depth map even in the dead of night. And it even uses ultrasonic sensors for that really close-range parking stuff. By fusing all these sensors together, the car's SLAM system gets an incredibly rich, robust, and reliable model of the environment. Once all that data streams in, the vehicle's AI brain goes straight to work. First, perception. The neural networks instantly classify objects. Okay, that's a pedestrian, that's a delivery truck, that's a red light. Second, prediction. Now this is definitely the hardest part. The AI has to anticipate totally erratic human behavior, like say a kid suddenly chasing a bouncing ball out into the street. Third, planning. The system calculates multiple potential trajectories, scores them for safety and efficiency, and then finally executes the steering and braking commands. Perceive, predict, plan, act. All of this happens seamlessly, continuously, over and over again in literally a matter of milliseconds. So we've seen how SLAM and LiDAR evolved from basically solving a theoretical robotics puzzle into these incredible technologies that map our living rooms, guide surgical instruments inside the human body, and drive massive cars through dense, chaotic city traffic. The hardware is getting smaller, it's getting cheaper, and it's getting vastly more powerful. Meanwhile, the algorithms are learning from millions of miles of real-world data to handle even the weirdest, most unpredictable edge cases. The technology is here, and it is constantly, rapidly improving. So, as these invisible digital brains become increasingly flawless at mapping and navigating our physical world, the final question really isn't about the technology at all. It's about us. Are you ready to hand over the steering wheel to an algorithm?